So, welcome student to the next class of Introduction to Nonlinear Optics and its application. So, in this class we will going to study one important concept which is optical parametric oscillator. So far we are dealing with optical parametric amplification. So, we find that some kind of amplification is there under this nonlinear process. So, we will try to find out that how to use this kind of amplification in real practical fields. So, optical parametric oscillator is a light source similar to the laser, and also like laser we have a resonator here, that means the light is bouncing inside this cavity, but here it is not based on optical gain, rather parametric amplification process or nonlinear effects are involved in such kind of oscillator or such kind of amplification process. So, in the laser we know that we have a metastable state, and when we excite the system which has a metastable state, so we get some kind of gain. So, we have coherent radiation under that, but for OPO we will get something different. So, we will have pump, and this pump will be splitted into two part, and this two part is essentially gives you two different frequency with the energy conservation condition that omega p is equal to omega s and omega I. Now, omega is a signal that will going to amplify, and omega is the idler that will going to generate. Now, this amplification of signal we discussed in our last class, and now we will going to use this amplification and make an oscillator, so that I can amplify and use this as a laser source. Well, optical parametric oscillator has some important features that let me describe very briefly. That it has the wavelength versatility. So, you can generate ultraviolet to mid IR range wavelengths. In terms of frequency, it is terahertz limit if I generate in mid IR. So, wide range of wavelength one can generate, and it depends on the material to material. Also, the temporal versatility is there. You can generate CW to femtosecond kind of pulses out of this resonator, and in operation domain is normally room temperature and greater than that, and also we have high power and pulse energies out of these optical parametric oscillators, and it will give a legitimate amount of power in the limit roughly 30 watt to 200 millijoule in terms of energies, and also it is a very high efficiency material. So, 50 to 90% efficiency we will have, which is very large compared to any kind of laser. It is compact and solid state design. So, we have a compact material, or we have a compact solid state system through which we can generate this kind of amplification, and the process is entirely done by the material, the nonlinearity of the material, and it will generate different frequencies, and we will amplify, one can amplify these frequencies by making a cavity. So, we will discuss that, but also there are few drawbacks are there. I should not say drawbacks, but these things one need to careful enough. First of all, the stringent material requirement. So, if I make an optical parametric oscillator, then obviously we need to choose proper optical material having high amount of optical nonlinearity, and also the transparency should be there, because at the end of the day I need the light to come out from the system, and phase matching condition is very important here, because in the previous classes we find that If the phase matching is there, that means if delta k equal to 0, then we have a good efficiency, otherwise the efficiency drop down radically. And then damage threshold is something that we need to take care of, because we need to pump from the outside. So, if the material is such that it will not going to be it's going to damage for this launching pump power, then it will be difficult. So, the damage threshold is something that we need to take care of. This is under material requirement. Also the stringent pump laser requirement, because in this case also we need to excite the system by launching some kind of pump, and then because of the nonlinearity, the vibration of the dipole inside and some kind of frequency mixing is there. So, we have the splitting from one photon, pump photon, it will going to split to two different photon of frequency omega s and omega I by making energy and momentum conservation. So, strong pump laser is still required to excite such kind of system. So, high spectral and spatial coherence is required, and also sufficient high energy of the pump is required, because in order to excite the nonlinearity, the second order nonlinearity, normally the second order coefficient is small. So, in excite the second order nonlinearity, a prime consideration is that I should excite the material by external light, and this excitation should be sufficient to generate second harmonics or the second order effect. So, that is why the pump intensity has to be very high. Well, after this thing, let me briefly describe the optical parametric oscillator. So, you can see in this figure we have a nonlinear crystal here, and we are launching some kind of pump outside the system, and this pump is now enter into the system. These two things are mirrors, and these mirrors should have some kind of reflectivity, and if when we put this kind of pump inside a nonlinear crystal, so what happened, this pump will split and generate two different frequency omega s and omega I, that we know. So, now omega s is now generating here, and what happened for this particular mirror, the reflectivity of the frequency at omega is very high. So, it will start vibrating. So, start making a round trip oscillation, the field associated with omega s will make a round trip oscillation, and we have some amplified omega s and omega I will generate, but this omega I will come out because the mirror is made in such a way that it only make a round trip oscillation for the frequency omega s. Since only one frequency is making a round trip, we call this singly resonant oscillator. So, this singly resonant oscillator can amplify only one frequency, and in this case it is omega s. Now, also when it is vibrating, so the mode of frequencies are there. So, we know that in an oscillator, if I consider this is oscillator, so L is the length of the oscillator, Ns into L is the length of optical length of this system. So, the modes that will be inside the system has to be multiplication, this quantity optical length has to be multiplication of lambda s by 2 multiplied by m. So, these are the modes that should be oscillating inside the system. So, now if I consider this term, then we can find lambda s, the oscillating modes, which is function of m, can be replaced by 2n s divided by m. From this also we can find out what is the frequency, corresponding frequency from lambda to frequency conversion, and finally we can, from the frequency we can find out what is in terms of angular frequency omega s. So, angular frequency omega s suggests that pi c divided by L n s, this is the quantity multiplied by m, that are the corresponding modes that we have inside this system. So, these are the modes that will going to vibrate inside this system. Well, for optical parametric oscillator, under this system, for singly resonant case, we need to find out what is the condition or what is the pump condition for which we can have amplification. This is the old problem we are doing, but in a new way, because here the fields are moving and making a round trip. So, in order to find out what is the threshold value for generating any kind of amplification that is coming out from this optical parametric oscillator, we need to solve the differential equation once again, and here we explicitly consider delta k equal to 0. That means there is a phase matching. So, under phase matching we have two equations. So, quickly we solve this. This is the different, these two differential equation we solved several times. Here the pump is constant. So, under this thing we can have a double derivative of this quantity and we have a double derivative of E I. We just replace this. When I replace, we will have an expression like this. So, we will have a differential equation for the signal which is going to amplify like this g square E s. So, this is the differential equation. We know we already had this in our previous treatments. So, I am not going to discuss this in detail. The solution is also well known. So, when we have this expression in our hand, we will have a solution like cos hyperbolic and combination of cos hyperbolic and sin hyperbolic. So, once we have the solution of cos hyperbolic and sin hyperbolic, then the next thing is to put the boundary condition to find out what is going on. So, when we have a boundary condition, then readily the first boundary condition suggests that the A should be E s 0, because E s as 0 is 0, because we have something here to start with. So, some amount of omega s is here, and then it will going to generate from this quantum noise. Actually, we can generate these things, and then in order to evaluate B, we make a derivative of that quantity at z equal to 0, it is 0. So, that suggests we have B equal to 0. So, we will finally have our old expression that we have been using for last few classes, that the signal will going to increase and the growth is something like that, the evolution of the signal is something like that. It will be changing in the form of cos hyperbolic g z. Well, once we have the expression, then the next thing is, this is a very important slide. The next thing, in order to find the threshold, we need to find out what should be the value of these at different points inside this nonlinear crystal. So, this is the cavity. Inside the cavity we have the length of this cavity cell, inside the cavity we have the nonlinear material, and now we point. So, this is the pump that we are launching. This is the pump we are launching, and we consider the reflectivity is R here, and reflectivity R1, and reflectivity of this mirror is R2 here. We know our electric field for signal is evolving with this expression. So, E s 0 cos hyperbolic z z, this is the expression for signal, and now at this point we consider, at this point the signal is E s 0, that we know. So, E s at z equal to 0 is E s 0. This is our boundary condition, and we use this boundary condition. So, once it is known, the next thing is that I need to find out when it make a round trip. This is the process of round trip. At each point, what should be the value of our electric field. I write, if this is electric field, the value of electric field at z equal to 0, E S1 is the electric field of at z equal to L point. So, from here to here we find that there is a change of electric field. So, this electric field value I now note as E S1. Here we have a reflection. So, we need to take account of that also, and after reflection of from this mirror the field may change, and I designate this field at ES2, and now again it come back to this part of the mirror. I write it as ES3 because it is coming from here to here, and then again it reflects, and when it reflects I write it as ES4. So, ES4 I start with ES0, it goes here, reflect, goes here, reflect, and this is the final field I have. So, now the condition is, if we need some kind of gain, then ES4 has to be greater than ES0. The amplitude part has to be greater than ES0, because if ES0 is greater than ES4 is greater than ES0, then only we can say that this resonator is amplifying the signal. So, our aim is to find out, if I start with this expression, or if I consider this is my goal, then what should be the value of the threshold pump to get this. Because when we going to evolve, we know the G term is sitting here, and inside the G the information of the pump is embedded. So, whatever the value, whatever the condition we have, this condition we can write in terms of G, and then we can find out what is our threshold condition. So, that is the aim. Well, if we understand properly that this ES0, E10, these values are here, then we can write what is the value of ES1, ES2, ES3, ES4 one by one. First value ES0 is ES0 because we start with that. So, if I put z equal to 0 in this case, so we will have ES at z equal to 0 is ES0. So, first term is okay. What about ES1? That is the next important thing. So, we have the expression here. So, if I want to find out what is ES1, I just need to do that at z equal to L, we will find these things. So, this will be at z equal to L. So, that means ES1 is nothing but the field at z equal to L point, and when I put this, we will find ES0 cos hyperbolic of simply G L, because I need to find out the field at z point. So, I also figure out what is the field at this point. Now, this field, I have a reflection here at that point. So, when we have a reflection, we have ES2. So, ES2 can be represented in terms of the reflectivity of the mirror, and if I do, the ES0 is simply root over of R2 and whatever the field we have, because ES0, ES2 is simply the reflectivity multiplied by ES1. So, once we use this, then ES1 is this quantity. So, I just replace this quantity and I get also ES2. So, my ES1 is generated, ES2 is generated. The next thing is, if the field goes from this to this, what should be the value? So, ES3, the next to find out ES3. Now, this is quite interesting, because normally our tendency that if I want to find out ES3, so just put another value of whatever the value we have, that multiplied by this at z equal to L point will give you my ES3, but that is not the case. So, when the field is going from here to here, you need to consider that at that path from here to here, which is going to opposite direction, delta k is not equal to 0. So, let me write clearly. So, at this part, delta k is not equal to 0. Why delta k is not equal to 0? Because our phase matching condition suggests that delta k, if I write in vectorial form, because this is better, delta k is equal to kp minus, so let me write once again, delta k is kp minus ks minus ki. In vectorial form, this is my delta k. So, when delta k equal to 0, that means kp is equal to ks ki. But here, since the wave is moving in the opposite direction, so this expression, in this expression, field pump is moving in this direction, idler moving in this direction, but here in this, if in this case I consider delta k equal to 0, for this path from here to here, the field is moving in opposite direction. So, as shown here as a note, delta k is not equal to 0, because since the field is moving in opposite direction, for this expression I need to put one plus here, because it is moving in opposite direction. As soon as I put a plus sign here, we should not write delta k equal to 0, rather delta k is not equal to 0. Since there is no phase match in this case, so there will be no amplification, and also if I consider there is no loss into the system, so what eventually we find in ES is the same value that we have here. So, ES3 is eventually ES2, the same value we will have, because there is no phase matching. So, there is no amplification because of that delta k not equal to 0 condition, and we will eventually have the same field if I consider there is no loss. If it is loss, then obviously there will be exponential term associated, exponential losses term associated with that, but for the time being we consider there is no linear loss. Well, once we have this, then again it is reflecting. So, when it is reflecting, so we will have ES4. So, ES4 is root over of R1 R2, whatever the value we have, and root over of that, root over of R multiplied by that. So, we will eventually have ES4 like this. So, starting from ES0, we now come to ES4 in this particular structure. So, once we have this in our hand, then the next thing is to find out the threshold condition. So, the threshold condition, as I mentioned, when ES is at least equal to E4, ES4 is equal to ES0, that means this value and one after one round trip this value, if these two are same, then that is the threshold condition. But in order to amplify, as I mentioned, ES4 has to be greater than ES0, but equal to is a condition which we call the threshold condition. So, when I put this value, because ES4 I derived and it is this, and when I equate these things I write G threshold, because G is now replaced by G threshold. So, this is equal to ES0. So, now ES0 will cancel out. So, we have cos hyperbolic of G threshold L is equal to 1 divided by root over of R1 and R2. Now, root over of R1 and R2, this quantity is the reflectivity, and reflectivity is very high and very near to 1. So, this quantity is very near to 1, this root over of R1 and R2. So, we have, if this quantity is 1, if I expand this cos hyperbolic term, then we have 1 plus, under this approximation we have 1 plus G threshold square L square divided by 2. This is just the expansion with this condition that R1 and R2 are very high. So, G threshold is equal to this root over of 2 L, and G threshold square, which is related to the EP threshold square, which is nothing but the pump of the pump power, is this. So, pump power threshold is replaced by EP mod square threshold, which now have GTH. So, I just replace this GTH and finally come to this expression. I want the student to please do this calculation once again by your own hand, so that you can understand what is going on, but all the steps are given here. I am not explaining each and every step, because this is a simple algebra and I believe you are quite capable to do that. But the important thing is that I can now find a threshold power. This threshold power is really required to amplify the signal inside the optical parametric oscillator. So, today we find, so we will now going to conclude today's class. So, today we study in detail about the optical parametric oscillator and give an example that for singly resonant oscillator how the threshold power can be achieved, and in the next class we will extend this concept and try to find out, instead of vibrating one wave which is at signal, if I want to find out the vibration of two wave, which is called doubly resonating oscillator. So, what are the consequences of that, and how to find out for two resonating wave, how to find out the threshold condition, etc., that we will do in the next class. So, with this note, let me conclude here. Thank you for your attention and see you in the next class.